when you're factoring and there's no coefficient on the x squared, it's just about the factors of 21 that will give us a 4, or the factors of 30 that will give us an 11. But when we have a coefficient, we have to deal with this as well as the 20. Now, the easiest way I know is to use grouping. And so what we do is we say 6 times 20. So that's the first number and the last number, and I multiply them together, and I get 120. And then I want to find factors of 120. And I wanted to give me a negative 23. Okay, and since 120 is going to be positive, it's going to be a sum. So I'm going to need two negative numbers that'll multiply and make 120, but that will add up to negative 23. So I'm going to make a factor table. And I'm just going to start trying to figure out factors of 120. And the easiest one is 2 and 60. If they're both negative, they'll multiply to make 120, but they'll add up to negative 62. So that's not going to work. I can do negative 4 and negative 30, but that's going to be negative 34. Also not going to work. And to get that 4 and 30, I divided 60 by 2 and brought that 2 over. So I'm going to do the same thing. I'm going to divide 30 by 2, and I'll get, not negative 6, sorry, negative 8 and negative 15. Negative 8 and 15 will add up to negative 23. So those are the factors that I want to use. Okay. So then I'm going to replace the middle term with these factors. So I'm going to go in now, and instead of having 6y squared minus 23y, I'm going to do 6y squared minus 15y minus 8y plus 20. And the reason I put the 8 with the 20 is both 8 and 20 will divide by 4, and 6 and 15 will both divide by 3. So I put those together just because they had numbers in common. And I could have gone the other way, and I could have done 6 and 8 and divided by 2, and 15 and 20 and divided by 5. Like, it, either way will get you the same answer. So then I group and factor out the GCF. Oops. Keep going ahead of myself. Okay. So 6y and 15y will both divide by 3y, and I get 2y minus 5. And then 8 and 20 will both divide by 4. And I get negative 2y plus 5. And my numbers match, but my signs are wrong. So if I change this to a negative 4, then that gives me a positive 2y and a negative 5. And now they match. And then my fourth and final step is to so then from here I'm going to take that 2y minus 5 and then this 3y and minus 4. And so this is the factored form. if you have positive, 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 your factors will be positive. If you have positive, negative, positive, your factors are negative, and in both of these cases, you're looking for a sum. If you have positive, negative, negative, you have one factor positive and one factor negative. And it's still a sum, but it's kind of a difference, right? Because one's positive and one's negative, so you're subtracting the numbers and keeping the sign of the larger side. So if you have a negative in the middle, this is going to be the larger factor. And if you have positive, positive, negative, you're still going to have one factor positive and one factor negative. But in that instance, this is going to be the larger factor because you want a positive number in the middle. So that's just kind of a way to know what signs your factors need to have. Okay, so I'm going to take the 15 and the 1. I'm going to multiply them together, and ooh, it's 1. That's easy. Or not 1, 15. And so then I'm going to look for, I have positive here and negative here, so I'm going to be looking again for negative factors of 15. You want to do the giant X? Yeah, absolutely. We can do the giant X. It still works. Do the big giant X, and we want to multiply. Did I put the multiplication on the bottom last time? I think I did. Okay, you want to add to be 15, and you want to multiply to be negative 8. Can you guys think of any? Yeah, negative 5 and negative 3. And so then I'm going to take that 15x squared, and I'm going to replace this negative 8x with negative 5x, negative 3x, and plus 1. And I'm going to factor a 5x out of this first group, and I'll get 3x minus 1. And I have 3x plus 1 over here, but I want it to be 3x minus 1, so I'm going to factor out a negative 1. And I get 3x minus 1. Does that make sense? So then I'll take that 3x minus 1 out, and then I have 5x minus 1. Okay, so we're going to do negative 12 times positive 15, and thank you. And so now I'm going to look for, in my big giant X, things that will add up to 8 and multiply to make negative 180. Now I have a negative here but a positive here. So that means I'm going to need one factor to be negative and one factor to be positive. And they're going to basically have a difference of 8. So let's think of factors of 180. 9 and 20, but those have a difference of 11.
10 and 18.
Okay, cool. 10 and 18. So I want my 10 to be negative because I want a positive 8. So I'm going to do negative 10, positive 18, and those will add up to give me that positive 8. Yeah. Which side? No, just so long as one of them's plus and one's multiply, you can put the multiplication on top and the adding on the bottom. And then it doesn't matter which side you put these on either. These? Yeah, it doesn't matter. I could easily do it this way too and put that as 180 and this is 8. No. That does matter because you want them to multiply together to make 180, but you want them to add together to make 8. So that part matters. Now you don't have to put the multiplying and the plus in there if you don't want to. I just do that so that when you look at this later, you know what was going on. If I was factoring this myself, like if it's my homework assignment, I'm just going to go like this. And then I'll put the -10 and the +18, and I've got it. I don't need those symbols, but I tend to write more in the notes than you guys actually need to write down, just so when you look at it later, it makes more sense. Okay, so I'm going to replace 8 with -10 and +18, and you get to decide. I have -12x squared. Do you want to put the 10 or the 18 with the 12? It really doesn't matter. Okay. Okay, because here I can divide by 2, and if I had put the 12 and the 18 together, I could have divided by 6. So these are both negative and these are both positive. So I'm going to pull a negative out of the front. I'm going to pull -2x, and I'm going to get 6x minus 5. And then from 18 and 15, I can divide by 3, and I'm going to get 6x plus 5. That's a problem. Hold on. I knew I made a mistake. See, that's how you can tell if you've made a mistake or not. Like, I forgot to pull the negative out from the 10, so this should have been a +5, not a -5. So as soon as I saw that, I knew that I had made a mistake. There you go. No, because if I divide both of these by -2, they both become positive. And then here, these were already positive, so when I divide by a positive number, they stayed positive. I just had made a mistake when I first did my division. And it's really easy to do that, but it's blaringly obvious at that point because they didn't match, and so I knew I had made a mistake. So I had to find it. We've got the 12x squared minus 4x minus 5, so we do 12 times -5, and that gives me -60. Because this is negative, whenever this ends up being negative, you know you're going to need one positive and one negative factor. Okay, so if I do the big giant X, I want two numbers that when I multiply them will give me -60, and when I add them will give me -4. So they're going to have a difference of 4. So 60 is 2 times 30, 4 times 15, 12 times 5, 6 times 10. 6 and 10 have a difference of 4, right? So -10, +6 to get that -4. Oops, minus 6x plus 6x minus 10x minus 5. So the -4 was replaced by the 6 and the -10, and then I can divide both of these by 6. So I get 2x plus 1, and I can divide both of these by -5, and I get 2x plus 1. Pull down that 2x plus 1, and then the 6x and the -5 go in the second set. The product property is one of those properties that when you understand it, you go, well, duh. Basically, if you have two things multiplied together and it equals 0, then x equals 0 or y equals 0. Makes sense, right? If you multiply two things together and the answer is 0, one of those things had to be 0. So we use this property solve equations. Okay. We have this formula here that tells us the height of a javelin. You guys know what a javelin is? On the Olympics, it's like the big long stick that they throw, and then it like flies through the air and then goes into the ground. So t is time in seconds after it's thrown, and we want to know how long is it in the air. Okay, well, height, if it's on the ground, the height is 0. And that's what we want to find out. When is it back on the ground? So we're going to set this equal to 0. Okay, and that tells us when it's back on the ground. And now we need to solve it. So the first step is to set equal to 0. The second step is to factor. All right, so I'll make my big giant X. And I have negative 16 times 5, which is going to give me negative 80. And I want factors of 80 that will give me a 79. Well, that's 80 and negative 1, because 80 plus negative 1 is 79. And I already know 16 will go into 80, so that makes that next step kind of easy. I'll put those two together. And if I factor out my 16t, I'll get negative t plus 5. And if I factor out a 1 here, I get negative t plus 5. So I have 16t plus 1 times negative t plus 5 equals 0. After you factor it, you want to set each equal to 0, because my product property tells me if this times this equals 0, then at least one of them equals 0. And then after that, you'll solve each. So 16t plus 1 equals 0, and negative t plus 5 equals 0. So 16t equals negative 1, or t equals negative 1 over 16. And then when I come over here, I get negative t equals negative 5, or t equals 5. Now, which one is correct? In this instance, we're talking about time. T is time. And time is never negative. So this is not valid. So our correct answer is 5. So it's 5 seconds. So when the guy throws the javelin, it's going to be in the air for 5 seconds before it lands. Example. And we actually just factored this, but we need to set it equal to 0. So to do that, I'm going to move this 5 over, or I can subtract 5 from both sides, however you like to look at it. And that will give me 12x squared minus 4x minus 5 equals 0. We have our big giant X. 12 times negative 5 is negative 60. factor. And I want a -4. And we had already figured this out, so I have -10 and +6. So I have 12x squared minus 10x plus 6x minus 5 equals 0. I can factor 2x, so I get 6x minus 5, and I can factor out a 1, and I get 6x minus 5, and that gives me 0. So I have 6x minus 5 times 2x plus 1 equals 0. Okay. So I'm going to set each of those equal to 0. And then I'm going to solve them. And you're going to get 2 answers. And it's nice property of... You could, yes. The nice thing about this is if you get a squared, if squared is your highest exponent, you're going to get 3 answers. Or 2 answers, I'm sorry. 2, 2. If you had a 3, you'll get 3. If you have a 4, you'll get 4, etc. That's kind of a nice little thing. Or sometimes you get 1 repeated answer. So you get the same answer twice, but it's still 2 different answers. All right, so when we talk about complex numbers, first we have to talk about square roots. And in order to talk about square roots, it's best first to talk about squares. So I'm going to fill this chart out really quickly and give you guys time to write it down. Okay, so let's look at perfect squares. The square root of a perfect square, well, 25 is 5 squared, so the square root is 5. Obviously, you don't have to write in this middle step, though. So 144 is 12 squared, so the square root of 144 is 12. Square root of 625 is 25. Square root of 361 is 19. Square root of 225 is 15, and square root of 289 is 17. Thanks. 17. So the square root of perfect squares is that number that squared gives you. Questions on that? Okay, that part's pretty straightforward. Complicated. Now, there are 2 ways to simplify non-perfect squares. The first way is to recognize the perfect square inside and say, oh, well, 200 is 2 times 100, and 100 is a perfect square. So I can take the square root of this perfect square, which is 10, and I can leave the 2 behind because it's imperfect. But maybe you don't recognize the perfect square inside the square root. So that's method 1, is to see the perfect square in there, but maybe you don't see it. And you can make a factor tree. And I can look at this number 99, and I can say 99 divides by 3, and then 33 divides by 3, and then 3 and 11 won't divide by anything further. And I can say, oh, here's a pair of 3's. So every pair Every time I find a pair, that's a perfect square. So what I can do is I can pull one of those out. The other one just kind of goes away. So I pull that 3 out, and whatever wasn't a perfect square gets left behind. So that 3 was perfect, so I could pull it out, and that 11 wasn't, so I leave it behind. Uh, 324. It's even, so it'll divide by 2. And that's 162.
It's
18.
It's equally 18.
Oh, did I do a 3? Did I do a perfect square? Darn it. Well, let's pretend it's not. Yep. See there. And you don't have to keep going when you get a matching, like if you get a V that's perfect match. Yes, I could take each of these 9s and make them 3 by 3. But I don't have to because it's already a match. So I have a 2 that's perfect and a 9 that's perfect. So I can bring out a 2 and I can bring out the 9, and there's nothing left behind in this instance. So it's 18. I didn't mean to make it perfect. Darn it. Typo. 1440. Well, 10 times 144, and yes, 144 is perfect, but let's say you don't recognize that. Well, 10 is 2 times 5, and 144 is 2 times 72, and 72 is 2 times 36, and 36 is 2 times 18, which is 2 times 9, which is 3 times 3. And then I start finding pairs. I have a pair of 3s. I have a pair of 2s. I have another pair of 2s. And then I have this 2 and 5 that don't pair off with anything. So for each one of these pairs, I'm going to bring out 1. And then that 2 and that 5 that were left behind stay underneath. And then I multiply everything back together. 12 square root 10.
I did it like 36 and 40, but then I did 6 radical 40 and then factored the 40 and still got the same thing.
That's fine. There's more than one way to do this. And there's this theory called the fundamental theorem of arithmetic. And the fundamental theorem of arithmetic is that every number can be factored to a unique set of primes. So if I take 1440, I can divide it by 2, I can divide it by 10, I can divide it by 3, I can divide it by 36. Like however I start the factoring, it'll always end up being the same set of factors at the end. So there's always more than one way to do these because of that. Okay, so here's what happened with imaginary numbers. There were all these like engineers and mathematicians, and they kept doing problems, and they would get to square root of a negative number, and you can't take a square root of a negative number, right? Because if I take two positive numbers and I multiply them together, or like 5 squared is 25. And if I do negative 5 and I square it, that's negative 5 times negative 5, it's positive 25. There's no such thing as a negative perfect square. And they hit this wall, but they needed to keep going further. So they came up with the imaginary number system. This is made up. It does not exist. Not for real. So that's where imaginary numbers came from, and imaginary numbers are just that. They're imaginary, and it's the square root of negative 1. That's the basis for the whole thing. And the square root of negative 1 equals I. I for imaginary. Pure imaginary numbers are only imaginary. So we have things like 5i and 3i, or just I, or negative 2i. These are pure imaginary. And that comes from taking square roots of negative numbers. So 25, the square root of 25 is 5. So it'll be 5i. And the square root of negative 100 is going to be 10i. So you take the square root of the number, and then the negative becomes an I. Same principle when you have a non-perfect square. 27 is 3 times 9, and 9 is a perfect square. So I'm going to take the square root of that 9, which is 3. I cannot leave the negative underneath, so I pull out the negative, which is I, and then this other 3 gets left behind. Yeah, let me just pause it real quick. Okay, 216, not perfect, so I start factoring it. I get 2 times 108, which is 2 times 54, which is 2 times 27, which is 3 times 9, which is 3 times 3. And I start grabbing pairs. So I bring out a 2 and a 3 and an I because of the negative. We can't ever leave the negative behind. It always has to be an I. And then a 2 and a 3 get left behind. Right here, these guys get left behind. So I have 6i root 6. We have to talk about products of pure imaginary numbers. Well, if the square root of negative 1 equals I squared equals negative 1. And I to the third, well, that's I squared times I. So that's negative I. And I to the fourth, well, that's I squared times I squared, which is negative 1 times negative 1, so that's positive 1. And I to the fifth, that's I to the fourth times I, so that's positive I. And then that's the pattern. Because if I go to I to the sixth, I get back to a negative 1. I to the seventh will give me a negative I to the eighth will give me 1. I to the ninth will give me I. So it's I, negative 1, negative I, 1, positive I. So if you start, let's say I said something like I to the 17th, or let's go bigger. Let's say I to the 25th. If I start here and I go, okay, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So if you have these first 4, you can just rotate through them and just count until you get to the one you need. Does that make sense? Want me to do it again? Okay, so we were looking for I to the 25th. Let's try a different one. Let's try I to the, give me a number. Any number. 10? Okay, 10. 2, right? I squared 2, 3, 4, 5, 6, 7, 8, 9, 10.
Negative 1.
Yeah. So if I asked you for I to the 19th, I'd start at 2 again. I go 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I to the 19th would be negative I. Does that make sense? So you can just count through those 4 to find it. When I multiply pure imaginary numbers, like in this case, I'm only going to have 3 or 2 i's. So I multiply the numbers, and then I multiply the i's. So what I get is 5 times 3, that's negative 15 I squared, because I times I is I squared, except I squared is negative 1. So this gives me positive 15. You never want to leave exponents on your i's. You can have an I by itself, but you never leave exponents on them. So you need to go through this to find it if it's more than just 1. If I have my roots like this, well, 6 doesn't have any perfect squares in it, so this is I root 6. And 15 doesn't have any perfect squares in it, so this is I root 15. So you want to take those i's out first. And then I times I is I squared. And the square roots multiply together. So this is going to be negative 1 times the square root of 60. No. Yes, no. 90. Right? 90? 90. Okay, 90. And 90 will reduce, or can be simplified because there's a perfect square in there. Because it's 9 times 10. And 9 is a perfect square. So this will be negative 3 times the square root of 10. Equations with pure imaginary solutions. What we want to do is we're going to solve this. It's 256 divided by 4. Let me just double check that real quick. It does. Okay. So I'm going to subtract 256 from both sides. And I'm going to get 4x squared is equal to negative 256. And then I'm going to divide both sides by 4. And I'm going to get x squared is equal to negative 64. Okay, so I want to isolate the x squared. And then I'm going to take the square root of each side. And I'm doing that because there's no other x's. So I have x squared equals negative 64. So I'm going to take the square root of each side. And the square root of x squared is x. And the square root of negative 64 is 8i. So in the past, before you guys had I to use, you would have gotten x squared equals negative 64 and you would have had no solution because there was no such thing as a square root of a negative number. Now we do have a square root of a negative number. It's your little imaginary friend, I. So I'm going to do the same thing. I'm going to subtract 4 from both sides. I get x squared equals negative 4. And then I take the square root of both sides. So x is equal to 2i. Okay, complex numbers. So you have real numbers, which is all the numbers that we've been using. Whole numbers, positives and negatives, fractions, decimals, those are all real. Even irrational numbers like square root of 2, those are real, those exist. And then you have imaginary numbers, which is all based off square root of negative 1. And then you have what happens when imaginary and real come together. You get complex. So complex numbers have a real part and an imaginary part. And they look like a plus bi, or a minus bi. B can be positive or negative, where a and b are real numbers. But you've got that imaginary part. So this is considered to be the real part, and this is considered to be the imaginary part. When you look at a complex number, 5 minus 7i, this is a single number. Even though it's got two parts, but it's considered to be a single number. 5 minus 7i is one number, 2 plus 4i is another. So I can add those two numbers together. What we do is we add the real parts, and then we add the imaginary parts. So I'm going to add 5 plus 2, that's the real parts, and I'm going to add negative 7i plus 4i, that's the imaginary parts. So 5 plus 2 is 7. Negative 7i plus 4i is negative 3i. Again, we're going to add, I hate to do, I don't want to do the swoop like I do with FOIL because it's multiplying, so I'm going to do like this part thing. So I'm going to add these two numbers together, and 4 plus negative 5 is negative 1. And then I'm going to add these two parts together. 6 plus 2 is 8. Better? Okay. In complex numbers, you have to distribute the negative first. And then you add the real parts. And then you add the imaginary parts. So the first thing I'm going to do is I'm going to distribute this negative, and this is going to become 4 minus 8i plus negative 3 plus 6i. Okay, so that negative went inside. And negative times a positive is a negative, and negative times a negative is a positive. And then I'm going to add 4 plus negative 3, and that's going to give me 1. And then I'm going to add negative 8 plus 6, and that's going to give me negative 2. So sometimes they want you to find values that make things true. So what we have is a real part, right? And an imaginary part. And to be honest with you, this should be in parentheses. Sorry, that was a typing mistake on my part. So we identify that this is the real part here, and this is the imaginary part here. And real equals real, and imaginary equals imaginary. So the reals go together. And the imaginaries, let's make that a different shape so that, since you guys don't have color maybe, imaginaries go together. So I'm going to set real equal to real and imaginary equal to imaginary. And I can use that to find out what x and y equal. So 3x minus 5 equals 7. So this real part will equal that real part. And y minus 3i will equal 6i. Well, it's y minus 3 in parentheses, right? So the i's will cancel. So what I really get is y minus 3 equals 6. And then I can solve each of these to find out what x and y equal. So I add 5 to both sides here, and I get 3x equals 12. Then divide by 3, and I get x equals 4, and that's done. And then I come over here and I add 3 to both sides, and I get y equals 9, and that's done. Aren't here, but these parentheses are. So you can, this goes with the I, and this doesn't, so that can help you identify what's real and what's imaginary. Anything that's not attached to the I in a parentheses is part of the real part. So I can take this whole thing and call that real. Same with this side. So I can set those real parts equal to each other. 5x plus 1 is equal to 2x minus 2. Subtract 2x from both sides, and I get 3x plus 1 is equal to negative 2. Subtract 1 from both sides, and you get 3x is equal to negative 3. Divide by 3. X equals 1. So that's the real part. Then I can come back and I can take the parts that are attached to the I, and these are imaginary. Yes, thank you. Negative 1. Getting ahead of myself. So I can take those two imaginary parts and set those equal to each other. 3 plus 2y is equal to y minus 6. Subtract y from both sides, and I get 3 plus y equals negative 6. Subtract 3 from both sides, and y equals negative 9. Whenever I have two complex numbers together, you treat it sort of the same way you would have treated if it was like 2 plus x and 9 minus 3x or something. You're going to FOIL it. So I'm going to first, so 2 times 9 is 18. I'll write that a little lower. Then outside, so I get negative 6i. Inside is plus 36i. And then last, negative 12i squared. So step 1 is to FOIL. And then step 2 is to simplify. And remember, I squared equals negative 1. You can't keep it as I squared. So what this turns into is 18 plus negative 6 and plus 36 is plus 30i minus 12 times negative 1. So that I squared becomes negative 1. But I can't leave it like that either. It's not completely simplified. So this is actually 18 plus 30i plus 12. And 18 and 12 is 30. So when you multiply two complex numbers, you end up with another complex number. Most of the time, unless they're conjugates, which I'll explain later. sometimes it's necessary to differentiate between complex numbers, and so mathematicians will also use j. I and j are the same thing. So if I squared is -1, j squared is also -1. So I'm going to FOIL it. So I'm going to do first, and that's going to give me 6. Outside, -4j. Inside, -12j. And then last, positive 8j squared. But like j squared is -1, so this is 6 minus 16j plus 8 times -1. So this is 6 minus 16j minus 8. So this is -2 minus 16j. Because mathematicians like rules, they decided that it is illegal for I to be in the denominator. Not allowed. Just like you're not allowed to have negative exponents and you can't have square roots in denominators. They just decided it's not cool. It's not kosher. It's not legal. So in order to clear the i's, you have to multiply numerator and denominator by I. And this is if you have a pure imaginary in the denominator. So we have 5i. So if I multiply both the numerator and the denominator by I, what happens is I'm going to distribute that I to the numerator, and I'm going to get 4i plus I squared. And the denominator, I'm going to get 5i squared. Well, I squared is -1. So I get 4i minus 1 over -5. But we don't like this because it's out of order. And we don't like this because we don't like negatives in the denominator. So if I just change the order, I get -1 plus 4i over -5. And then to get rid of that negative in the denominator, you change all the signs. So this becomes 1 minus 4i over +5. And then it's nice and pretty and we like it. So here I have 6 minus 2i over 4i. So I'm going to multiply both the top and the bottom times I. And that's going to give me 6i minus 2 times I squared over 4i squared, which will be 6i plus 2 over -4, because that -1 times the -2 gave me the +2. And this has all kinds of problems with it. It's out of order in the top. It has a negative in the denominator. And 6, 2, and 4 can be simplified. So these are what's wrong with it in this format. So I'm going to deal with them one at a time just to make it easier. Actually. So if I bring this down here, I change the order. Okay, so that's fixing the first thing that was wrong with it. And then I'm going to change all the signs. Because that's fixing the second thing that was wrong with it. And then 2, 4, and 6 all divide by 2. So it's going to be -1 minus 3i over 2. And they have to all be able to divide by the same number in order to reduce it or simplify it further. If this was like a 5, you can't divide the 2 and the 4. It has to all 3 be divisible. A complex number in the denominator. Okay, you're going to multiply both by something called the complex conjugate. Okay, so here's how complex conjugates work. If I have a plus bi, the conjugate of that is a minus bi. These are conjugates of each other. So if this is a plus, I want to multiply by a minus. If this is a minus, I'm going to multiply by a plus. So you multiply by the opposite side, sign. So I'm going to multiply both the top and the bottom of this by 3 minus 6i. Okay, why do I do that? Because when I FOIL these, when I do the inside and the out, so I do first, right, I get 9, and then I do outside, I get negative 18i. I do inside and I get positive 18i, and those cancel each other out. So those middle terms will cancel. So I'm going to distribute the numerator, and I'm going to FOIL the denominator. And so I'm going to get 6i minus 12i squared over 9 minus 18i plus 18i minus 36i squared. And these two terms right here will cancel because they're opposites, and that's how we get rid of the I in the denominator. So I get 6i.
You're doing opposite signs. Shouldn't the 3 be a -2?
No, because it's only this sign that's opposite, so it's still positive times positive. Does that make sense? It's just that plus or minus that are. And then this is going to be 9 plus 36. So I'm going to rearrange the order. And 36 plus 9 is 45. And all three of these will divide by 3. So I'm going to get 4 plus 2i over 15. Now I'm going to show you one more of these two in just a second, so you don't have to FOIL it all out. I'm going to show you another trick.